for this afternoon session Professor Dirk Broer, who is coming from the Eindhoven University of Technology in Netherlands. And his talk, as you can see from the title, will be on responsive liquid crystalline networks and hydrogels. Let us welcome our speaker.
Thank you, Mr. Chairman, Mr. Ivan. Thank you for inviting me here. It's a real pleasure to be in Cambridge. My lecture will be on responsive networks. I mean, it relates to the topic that you heard this morning by Carl Motes and by Mark Warner. So we want to bring motion into liquid crystal polymer films, but we approach it more from an engineering point of view. So we try to make these things rather than model these things. So what you see here is a real measurement by interference microscope of a surface rather than a calculated one. It will be on liquid crystalline networks. If I have some time, if there's some time left at the end, I also will discuss liquid crystal hydrogels. I must confess that I'm a little bit nervous because I'm going to use the clicker system. And this is my first time, so I might need some help in this by you as well. Well, this at this moment should look familiar to you. If you have an ordered system, for instance a liquid crystalline system, and you bring the system to a state where it is somewhat less ordered, you bring some disorder in the system, then you might see changes in the geometry. And the geometry is therefore coupled to the molecular order. So in this particular case, if like the matches in the matchbox, if you bring them into a more random state, you will have contraction in this direction, and you will have expansion in the two other directions. And we are going to utilize this on a system that we worked out many, many years ago, and basically has been developed at that time to be used in, as for optical materials in liquid crystal television systems. And actually the materials based on this principle can now be found in every television that you buy on the market in one way or the other. And the principle is quite simple. You take a liquid crystal. We all know what liquid crystals are, rod-like molecules, for instance, but it can also be a disk, of course. And this particular liquid crystal is modified at its both ends with a reactive group. For a non-chemist, this is an acrylate group, and just if it comes in contact with free radicals, unpaired electrons, then it might initiate a chain addition polymerization. And if you do this in the presence of photoinitiator creates these free radicals, you very soon convert this material from its liquid crystalline state, from its liquid state, into a solid polymer just by connecting all these reactive end groups. So you go from liquid to a polymer. If the cross-link density is high enough, in the case of a diacrylate, so two acrylates, you form glossy polymers. And if you start with a monolithically oriented state at the beginning, you also end up with a monolithically oriented state in the polymer network. And in this case, glossy polymer, which means that the modulus is rather high, comparable to Perspex PMMA, which also has a modulus in the order of 1 to 3 gigapascal. Well, as we are using the low molecular liquid crystalline state to manipulate the molecules at the beginning, we can play many different tricks, so to say. We can decide to align them uniaxially, as is shown here, just by applying the monomer on a surface with some pre-alignment. For instance, you take a plastic coating, a polyimide coating, you rub it with a velvet-like tissue, and then this brings in microgrooves into the polymer, which are taken over in its orientation by the liquid crystal. Of course, orientation is then determined by the boundary conditions, and we can play with the boundary conditions, such, for instance, that the molecules are not uniaxially aligned, but make a twist over the thickness of the film. Or you can bring them into a bend or splay state, so it goes from planar gradually to a perpendicular state, which is called homeotropic state in the liquid crystal field. You can bring them into a tilt if you like, and you can add chirality into the molecules such that they start to rotate, yeah, and then the concentration of the chiral components determines the pitch of this rotation. And because we are using light to initiate this reaction, we can also use lithographic techniques to do it locally, just by using mask. You locally shield the area from light. You polymerize only in the illuminated states. That orientation is frozen in, and you still have liquid in the dark states, which can be converted into another type of orientation, or can just be made isotropic by heating. In this case, we have isotropic areas next to uniaxially oriented areas, and we are looking between cross polarizers. That's why these areas are nicely white. And just because of this combination of techniques, this is a nice example where you combine so-called bottom-up with top-down nano and micro structuring. Bottom-up because we are using the self-organizing capabilities of liquid crystals, and top-down because we can also use other techniques, for instance lithography or printing or whatever, to make a structure of another length scale. To demonstrate as a first demonstration that the ideas that you have been shown this morning are true, that is change in order results in a change of dimensions. We just did a simple thermal expansion coefficient measurement. Yeah? So normally if you measure the thermal expansion of a polymer material, you have to deal with a glass transition. I'm looking now for so. So if you plot the thermal expansion of a normal isotropic polymer versus temperature, then you normally see a behavior like this. So this is the thermal expansion below the glass transition temperature. This is the thermal expansion above the glass transition. So this is a glassy state, this is an elastomeric state, and of course you have a transition area. Well, our materials behave very, very differently. What you see here is that at low temperatures, that glass transition is around this area, you have already a difference in thermal expansion just because of the fact that during heating you go from a highly ordered state to a somewhat less ordered state. And then as soon as you pass the glass transition, it becomes even worse. So the disorder becomes larger. And you can even find negative thermal expansion coefficients in these materials. Actually, similar to what has been shown by Mark Warner this morning, and that is the contraction as soon as you start heating. And of course, simultaneously, the thermal expansion perpendicular should be larger. So apparently, the models of this morning are at least qualitatively true. Now we can make films of this material where we can change the orientation easily from planar at the top to perpendicular at the bottom. So this is a plastic film, a polymer film, homeotropic orientation here, planar orientation here. And now we are going to play the temperature experiments. And now comes the first question, actually an easy one, I think. Yeah. The question is what will happen if I heat up this sample. Yeah? A, will it expand but it remains straight? B, it shrinks and it remains straight. C, it curls and it wrinkles. D, it bends upward. Or E, it bends downward. So now I have to do something, wow, like this, and you can vote. Please do it a bit fast, otherwise I'm coming in time problems at the end. 10 seconds, 15 seconds is around about enough, yeah? Let's see what the answers are. I would have hoped for a better uniformity in this case. Okay, so what is the answer? I go back like this. How can this one? Oh, distribution. Oh, yeah. Okay, and then I click on this one, right? Yeah. Okay. Well, the answer is D. Yeah, because we have contraction at the top of this film, and we have expansion at the bottom of the film, which automatically should bend upwards. I forgot who voted for upwards. Okay, guys. Even Mark Warner has it just right.
So how did you apply the temperature here? What's the, I'm talking about the format data.
We just put it in the oven here, and we just cycle the temperature, and we took a photograph every now and then. Yeah, yeah. Another question could be, how did we make this splay in the polymer, of course? And that's by polymerizing it between two glass plates. One has gives an homeotropic anchoring. Yeah, it's basically glass treated with surfactant, and the other one gives a planar anchoring. It's glass treated with a polyimide, which is rubbed. Yeah, and then the boundary conditions of it. Yeah, sure.
Yeah. So if you give a heat using this oven, so why the top plate is shrinking?
Well, this whole film is in this higher temperature region. Yeah, because of the negative thermal expansion, you will have contraction at the top, and because of the positive thermal expansion, you will have expansion at the bottom. Yeah, and that basically can be seen here. If the molecules go from an ordered state to a less ordered state, yeah, it will contract in this direction, and it will expand in the direction perpendicular to.
Because of the anisotropy of the format expanding coefficient.
Exactly. Yeah. Yeah. So this is the game that we are playing, and in our group we are playing with different triggers. Temperature we already discussed. We play with the presence of moisture or gases. Even touch might be of interest, but today I will mainly also concentrate on the use of light to trigger these systems. And this was already shown this morning as well by the two former speakers. If you blend in an azobenzene molecule into the system, then this molecule can undergo a transition from straight to banded. Yeah? For the chemist, this is just the transist isomerization reaction of this molecule. The trans state has its absorption band around 360 nanometers. The cis state has its absorption band around 450 nanometers. If you excite this molecule in the trans state, it mainly goes to the cis state. If you excite the molecule in the cis state, it goes back to the trans state. And many groups actually in the scientific arena have shown many nice examples based on this system when you blend this into a polymeric system. So this is how we do it in practice. We take our liquid crystalline diacrylate in this case, and we just add, for instance, 5% of this diacrylate containing this azobenzene unit. Yeah? So you make just a homogeneous blend of these two materials, and they are just brought into this polymer network. Now we can try to measure changes in the dimension of this system. For instance, we can look what is happening if you what is happening with dimension parallel to the orientation when you expose it with UV light, and we just in this case start from this point, and then indeed we see the expected shrinkage for the same reason that we saw shrinkage when we were heating the sample. Yeah, and the direction perpendicular to that, you see the expansion. And in this case, if you expose it with visible light, so you address the cis absorption band of the system, then the reverse will happen. So you can play now with the dimensions of this system, which means that you also can use it again for this splay system. So we make a thin film with the splay alignment, but now also with the presence of the azo compound, and directly, if you expose it with UV light, you see a direct response in the direction that you would expect it to go. Yeah? These are experiments that are done by Casper van Oosten together with Mark Warner and David Corbett, and he actually was able to bring this to a state where you could make little elements based on this system just by simple inkjet printing. So he was using an inkjet printer to print little fingers on a substrate, fingers of about a few hundred micrometers large, and each finger has this plate molecular alignment. So if you expose these fingers, and this is in a scanning electron microscope, and here we are looking to the side of the fingers, but we expose them when they are immersed in water, just to prevent any temperature effect in the system. So the fingers are immersed into water, and just depending on the intensity of the light, you can adjust the amplitude of the deformation. Well, now we are using inkjet printing with this system. You can think, well, can you use more than one ink to print like you do at home? Huh? You print red, blue, and green next to each other. Well, the answer is yes. You can just make little fingers now which contain small elements which are sensitive to the UV light, as we just shown before. But in other part of the finger, we use another azobenzene dye, and they are sensitive for the green part of the spectrum. That's why they are red colored. And that means that depending on the wavelength that you are addressing the samples with, you can determine whether you are either exciting this part of the finger or the top of the finger. So you can directly bend like this, or you can bend only with the top of your fingers. And we thought it was kind of nice to make asymmetric motions in these elements, for instance, to use them for mixing and pumping in a microfluidic system.
You see what's written there, photoresponsive element, electrode?
This is the finger. These are also the fingers.
No, in the title, what's written there?
Ah, it's hidden by the... Oh, I'm now... We should find a solution for this. Let me see, Ivan. Elements. It's not so exciting, is it? Okay, now I have to do something else again to make the... Oh, this is really complicated. Now we are going to make it one step more complicated, not with the clicker, but with the molecular organization in our systems. So we are now grouping our orientation of the molecules around defect structures in the films, as discussed this morning by Carl Motes. So for instance, we can just decide to bring the molecules in kind of radial orientation around the defect, or you choose other orientations, but most of our work, and most simple to understand, is if we have the orientation in an azimuthal way around the defect like we see here. This is what you then see if you look through cross polarizers, yeah, where the molecules are parallel to one of the polarizers, they are black. When they are under an angle, they are white, and that also shows that you really have this nice orientation that you would like to have here. If you have an orientation like this, Carl and Mark could predict that you can make this cone simply by shrinking along the azimuth and expanding perpendicular to it. If you have an orientation like this, you will form this anticone, and in fact they have models where they also can predict all different types of orientations, but it was our task, of course, to prove whether they are really right in that. So we make this sample simply by making use of an alignment layer that is imposed by polarized light in a specific way, such that you get alignment, for instance, along the azimuth. So we have a polarizer, we have a mask, a slit mask. This is our substrate coated with a photo alignment layer, so it's an alignment layer in which the orientation can be set by exposing it with polarized light, and we rotate either the mask or the sample, so we gradually modify the whole substrate with an orientation layer. You can bring two of them together, you can fill it with liquid crystal, polymerize it, and then you have your film made. And this is an example of a deformation of one of our samples when we immerse it in hot water. And indeed, we started with a flat state, and indeed you can directly see the cone state. But nicer is it to see it in real life. When you trigger the sample with light, you directly see the cone being formed. This is by light, but also nice if you do it by heat. In this case, it's an infrared lamp, and we have added a little bit of absorbing dye for that wavelength into the system. And you directly see, again, you go from a flat state to a more nicely flowering state. Well, these are, of course, still simple structures. You can also make it more complicated, and that brings me to the next question. Suppose if we would make a system where we have twisted orientation, but we are alternating the twist. So here is it like this, here it is like this, here it's like this, and so on. So now the question is, and maybe I should already activate. I lost my clicker. What happened? No, then you see the answer already, or not? Oh no. What should I do? It's there. Sorry, I'm really an amateur in this.
What's the length scale of this relation?
Sorry?
What's the length scale?
In this case, it can be millimeters, but it can also be down to micrometers. Yeah? Yeah? So, we have to vote. A, bending upwards. B, bending downwards. C, forming accordion shape. D, complex wrinkling. Or the E, the film contracts and becomes thicker, but remains straight. Let's see. Most people go for C. I forgot what C was. I should do it like this, right? And then like this, okay. C, forming accordion shape. Well, that was the good answer. Here we have a piece of this film. In this case, again, we expose it with an infrared lamp and directly see it was first initially flat, but it starts bending up like a little worm. Yeah. Other experiment could be this one. Again, here we have a somewhat longer length scale. This is millimeters. So here we bring it again to this lamp, and you see that it goes from straight into this harmonica shape. If you do it sideways, then you don't see so much effect because the absorption is less. If you rotate it further, you will see the same. So now we have created geometrical changes. We created morphing, so to say. Now something different. We go to, sorry for this, the chiral pneumatics, what is underneath. We go to chiral pneumatics. So we go to systems where we have used chiral dopants to make this helicoidal order in the system. And just to give you an impression, I realize that not all of you are chemists, but just to give you an impression how these materials are being made. This is a typical composition of a film like that. So it contains molecules, rod-like molecules with these reactive groups. We play with diacrylates and with monoacrylates just to adjust the mechanical properties, the cross-link density of the system. These form cross-links, these form linear polymers. In order to induce the chirality, we added a molecule which has a chiral center, yeah, which makes it rotating. It's about 5% of this material is in the system. This is the azobenzene again. And of course you need a photoinitiator, but you need an optimized photoinitiator not to, during photopolymerization, addressing already the azo compound, otherwise you bring it already in a cis state in the too early phase of the reaction, so you should be sensitive at least for a somewhat higher wavelength. So this is a typical example of a composition that we are normally using. So now we have this system. We make a cholesteric film like this, and we are going to expose this by through a mask. So that brings me to the next question. Yeah? What will happen? Will it form bumps at the exposed areas, or will it form an indentation here? Just remember what the molecules might do in this case. Or will it just form a bump next to the exposed areas, in the dark areas? Or do you think, well, this is such a stable system, everything remains flat, or the film just delaminates, builds up so much stresses that it delaminates from the glass? I hope that everybody has given the answer. Wow. A very small majority for the forming the bump. If I wait, the other one becomes a majority or not. Can you decide, please? Plus the red button. You shoot at the right. Even. Well, the answer is A. It forms bumps at the exposed areas. Yeah. But the problem is you can hardly see it. As soon as you stop exposing it, it goes away. Yeah. So we have to do actually tricks to measure this effect. So it goes directly. If I stop exposing, directly becomes flat again. So we had to do tricks to measure the bumps, and that was as follows. So we took the sample, we pour liquid silicon rubber, uncured silicon rubber on top of it, then we expose through a mask. During exposure, the silicon rubber is curing in this case, and then when the silicon rubber is cured, we remove the light, the film becomes flat, but the structure is remained in the silicon rubber. So you can just put it off, and then just by interference microscope in this case, you can measure the protrusions. Of course, we are always afraid for that heat effects might affect our measurements. So we also have to build in some kind of reference experiment, and that is that we make samples which are exactly in composition the same, but we exchange the azobenzene for this tinuvin compound. This tinuvin has exactly, well, not exactly, but almost exactly the same absorption band, absorption behavior as our benzene. So if our azobenzene heats up, also this tinuvin sample should heat up. And this is the reference experiment, and you see that indeed, because of heat effect, we find some protrusions being formed as well, but they are as far not as high as the ones that are formed with the azobenzene. So we really are looking for a photomechanical effect in this case. Now the following question comes up. How is it possible that you find this bump? Because it is not so easy to understand. I mean, if you just think in the other terms that you have this order in this system that it will come up, is logical, but the whole system is really fixed in the XY plane. So the material that comes up is not supplied from its surrounding areas. Yeah? So something must happen with the density of this system. In fact, what you should expect that the density of this material in the exposed state is much lower as the density in the unexposed state. So that is a nice experiment to check whether that is really the case. And this is how we did it. So we made a little film of this material, and we immersed it in a water-salt combination. Yeah? And this water-salt combination, you can nicely and rather exactly set the density of the water. So you choose, for instance, water with a density that just is the density somewhat lower as of this film. Yeah? Then you expose this film with light, and because the density change, the density decrease occurs during exposure, this film with the azobenzene starts to float. Yeah? Not surprisingly, for reference, what you can see is that the tinuvin sample remains at the bottom. So it's again not a real heat effect which is dominating here. And then you stop exposing, and nicely the azobenzene sample starts to sink to the bottom again. And then just by repeating this experiment with many different solutions with different densities, you can actually determine the change in density during this photoisomerization reaction, which is about 10%, and this 10% really nicely corresponds to the high difference that we are creating in our films. So if you have a 10 micrometer films, we create protrusions of about 1 micrometer. Yeah? So this is, again, somewhat simplified, the model that we still have. So we have our liquid crystalline network system, straight azobenzene molecules, then you start exposing, they bend, and you form free volume. And the free volume is the origin of the density decrease. And as soon as you stop the light, it goes very nicely dynamically back. Actually, it goes very fast back, much faster than if you would record this isomerization reaction in the solution. Yeah? There are stresses which are promoting basically this backward reaction. Well, so far so good, but sometimes something else might happen. And that if you have a network which is less elastic as we wanted it to be. In that case, yeah, the molecules will not turn back to its initial flat state, but they get the opportunity to rotate further. So they go from the bended state, rather than rotating this part back to here, this part rotates back to here. And in light, this is a more stable state because light is coming from the top, and now it's in a non-absorbing state. So now it is not becoming excited as often anymore. Yeah? So there's a strong tendency of the molecules to undergo this reaction in a non-elastic network, and that would lead then to a non-dynamic system, but more to a permanent volume change. Brings me to the next question. How would you make a non-elastic network? Can you do this by polymerizing at low temperature without any post-cure of the system? Can you do this by polymerizing it in presence of an inhibitor in the system? Or can you do this by polymerizing it in the presence of oxygen? Perfect. I had hoped for an even distribution here. Because, in fact, now all answers are good. Yeah? Yeah? In fact, low temperatures during polymerization gives a low conversion, which makes also the network not really elastic. Inhibitors stop the polymerization, so you have a growing polymer chain. When it meets an inhibitor molecule, it directly stops. So the kinetic chain length of your polymers is shorter in that case. And actually, oxygen works as an inhibitor. So basically, these are also the 3 things that you can do wrong if you want to go to a dynamic surface, right? If you don't do your polymerization under the right conditions, you don't find dynamic protrusions being formed. But it's only a one-time event. And in this case, I have a demonstration for that. Actually, Danjin Liu has done all these experiments that I'm proud of today. She added a small amount of this inhibitor molecule, about 2% to the system. And then what you can see is indeed a permanent formation of these structures. And of course, by using different masks, you can actually also make different type of structures. Yes? But this is a one-time effect in this case. Yeah? So in this case, to get the protrusions, we had to expose through a mask system. Now the question is, can we also make systems that give protrusions without a mask? And that is by patterning the film. So I already told you at the beginning that we can make patterns just by lithography, by exposing the material through a mask. So in this case, we created area with the helicoidal order, the cholesteric order, or the chiromatic order. These are the screen areas here. And we have areas where we have this material polymerized at a somewhat higher temperatures, which are isotropic, and between cross polarizers they are black, and this is the mask that we were using for that. And in this case, we get structures formed like this. So in a sense, these areas go up, and these remain about at the same position. This is change of order by heating. We did this experiment together with Greg Crawford when he was on sabbatical in our group. This is done by Danqing, again, when you do it with UV light, again, in the presence of this azo benzene material. So really nice protrusion can be formed in a dynamic way again. This is, again, the deformation of around 10%. And Danqing was a little bit disappointed by this 10%, only 1 micrometer structures on a 10 micrometer film. So actually she came up with another idea. And this is the following. She made elements of this chiral nematic next to homeotropic elements. Yeah? And in that case, you can more or less envisage that they are helping each other. This one wants to shrink, according to the models that we showed this morning from Mark. This one wants to expand. So what you can hope for is that you see a larger protrusion. This is the film that she made. So black is homeotropic, yeah, apparently isotropic. Blue is the chiral nematic one. And what you see is also that we have transitions between one state or the other. It's difficult to go in an infinite small area from one state to the other. And these are the structures that we could grow in this system. Before it is flat, during it is structured, and after it is flat again. It goes nicely back to the initial state again. And for this we have a movie showing the elements. So here is how we make it. We fill a glass cell, partly modified with indium tin oxide. We orient the molecules by electrical field at the locations where we have the indium tin oxide. We polymerize the film in that situation. Then we remove the top glass plate. We have the azo compound into our material, and we can address it like this. So one area goes up, the other one goes down. Yeah, you can download this movie from YouTube, so to say. So this is, at the end, what we would like to make. And these are the expansion ratios that we can get in this case, yeah, in the order of 15%, somewhat more than the 10% than we measured before. And this is a sign that I have to ask the chairman whether I should continue with the hydrogels or whether, and this is a difficult time for you to do. What shall I do? Shall I continue? Shall I maybe use the clicker for that? No. A few words about on the liquid crystalline hydrogel. So we switch gear a little bit, yeah? So far we have seen liquid crystal molecules fully containing of covalent bonds. In this case, we have a molecule which contains hydrogen bridges, yeah? A less strong bond in the molecule, yeah? This system happens to be to have a symmetric phase, yeah? Molecules are not have only orientational order, but also have positional order, yeah? They are ordered in layers, so to say. So we can polymerize this system at the end groups again, but now having the hydrogen bridges, we can break the bridges and we can split the molecules like this. If you would do it like this, the whole system would disintegrate, and for that reason, we also now and then have brought in a fully covalent crosslinker into the system to keep the layers together. Well, you can, just shown by an infrared analysis, that this breaking of the hydrogen bridge removes quite nicely and complete, so to say. With X-ray, you can look to the changes in order of the system. This is the order before. This is the order after the alkaline treatment. And basically what comes out is that the whole system goes from a highly ordered system, in this case symmetric C-type. If you break the hydrogen bridges, it goes to a less ordered system of the benzoic acid groups, and the whole system fills itself with cations. If you look to the birefringence or the optical retardation, it grows from a high value, and as soon as you start breaking the hydrogen bridges, yeah, you are losing the order in the system, and the birefringence become low. But still the system is very ordered because you keep the layer structures, as was seen here from these small angle diffraction patterns. Yeah? And this is a cartoon of what we are making. The cartoon is not completely right because this suggests too much order in these areas. This is not present. but the layers are held together with these covalent bridges. And what you can do, for instance, is fill the elements with another ion, in this case barium, in order to make contrast in the transmission electron microscope. And what you then can see are the nicely lines of the elements filled, of the layers filled with the barium, which are in the order of 1 nanometer. And the periodicity is around 3 nanometer, and the periodicity is determined by the length of the bridging units. Yeah? Well, where can it be useful for? This is one of the applications that we are developing at this moment. It can very effectively absorb materials that you want to absorb. Yeah? In this case, in experiment, we have methylene blue. Yeah, it's a little bit cationic, so it wants to go to this negative carboxylic acid groups inside. We have a small piece of this film. We throw it in a solution containing this dye. We just wait a few hours, and all the dye is collected into the polymer film, right? If we have not opened, this is a reference, if we have not opened the pores by this alkaline treatment, it does not happen. So you have a very effective means to absorb materials. Other things that you can do with it is looking back again to actuating. Yeah? So this is the sample, planar and homeotropic. So planar, homeotropic means that the layers are in the plane of the film. Here we have the layers in one direction. And then if you do the treatment, what you see is that you have only uniaxial deformation. So we have swelling in water, and you have the uniaxial swelling of this material in this direction. In this case, the swelling in the plane is the same, and it is almost zero perpendicular to it. And here we have inkjet printed little elements of this film, and we show that the swelling occurs. In this case, the orientation is homeotropic, so the layers are in the plane, so material swelling should occur from outside inwards, which can be seen here as well. And this is a measurement showing the large anisotropy in swelling. And we are utilizing these systems now to make water deforming systems, triggered systems that respond to the presence of moisture in this case. And this is my almost last slide. That is, we are using now these systems together with the azobenzene that we just discussed. We, rather than using these covalent, normal covalent inactive bonds, we are using azobenzenes, which means that you can open and widen up and close the pores in the system. For instance, what can be seen in the dye take-up. In the cis state, the pores are closed, no dye goes in. In the trans state, the dye goes in nicely. And this is just a prospect of what we want to do with it, but we haven't done it yet, is to make kind of peristaltic gas transporting principles based on this system. So this is the conclusion and the message. I hope to have shown that liquid crystals are still alive. There's a life after the displays, so to say. This is the sprout of a sunflower. Our material is just the same, also directed itself to the direction of light. And we think we can develop a bright future in a variety of different applications. And these are the people that I should thank, the people in my university group, with my staff members, Bastiaanse, Schenning, and De Bijen. Some collaborations with Philips Research, Brown, of course, well, it's not Brown anymore, Cambridge, of course, and the University of Zaragoza. And I should mention especially Carlos Sanchez, who was a former postdoc in my group, but also was very helpful in making a number of the samples that I've shown to you. And with this, I would like to thank.
Very interesting and stimulating lecture. Do we have questions? Yes.
Thank you for your presentation. I had a question about these azobenzene complexes or polymers in general. How stable are they?
Not stable.
Not stable. So what happens then?
What we try to promote is our systems, for instance, in architectural applications, for Windows, smart windows, and so on. And the first question that the architects are always asking us, how long will it last? And then I say, well, in a sunny day, only 1 week. and then they walk out again. But at the moment, they are not stable enough for many of those applications, which means that we have developed alternative materials, and that is one of the topics that the chemists in my group are now working on, fulgides, for instance.
So instead of azobenzene compounds with these the nitrogens, you go for something different.
Exactly, yeah.
Okay, so if you make them in the lab and you leave them there in the lab for 1 week.
Oh no, if I leave in the lab for 1 week, it's not a problem. I can even leave them for years.
Okay.
Yeah, but if I'm exposing them to bright sunlight, I have a problem.
Yeah.
I'm also using them. We are also studying them for the use in microfluidic systems, for biosensing, for mixing, and so on. And then you are dealing with disposables, and then it is not a problem. I mean, you can really address the elements thousands of times, but again, not years.
Okay, good luck.
Yeah.
On that subject, if you go to stable dyes, does that mean you go out of the UV?
No. Because then the samples will become heavily colored, and that is not what most people will. Actually, azobenzene is already too much colored. Yeah.
So just last question that I would like to ask the next speaker too.
So in the very beginning, you showed the thermal expansion coefficient of ordinary and extraordinary axis. So how did you measure them separately?
It's by a TMA. It's just a commercial instrument of
So you did not measure it just from the manufacturer, the value?
No, we were using a commercial equipment, right?
Mm-hmm.
So we made the films ourselves.
Mm-hmm.
It's you have to put it into your system, and then it's in a quartz environment with close to zero thermal expansion, and you measure displacement in two directions. Yeah.
Okay, thank you.
Yeah. But it requires sensitive hands to do the experiments, I can say.
Okay, thank you.